so these shares sum to 1. Now, what are they exactly? So let's try to learn a little bit of something about them. And this is going to get to Casey's question.
But why, in this previous thing we just did, why isn't it S vector, S1 vector plus S2 vector equal a 1 vector?
So here, this is just your spending on labor and, let's say, natural resources relative to your total cost. But you also have all of this spending on every intermediate input. And so in this setup, what you're spending just on the common factors is not all of your cost. So what we're doing here effectively is purging all of the intermediate inputs out and looking at, once you do that, what is the actual share that resides in these common initial factors.
But I thought you said earlier that these shares were going to sum to 1. And I thought that made sense because ultimately you're only using 2 factors, maybe directly or indirectly.
Right. So that's here. The new shares are these shares. I minus phi inverse times S1, that's a share. I minus phi inverse times S2, that's a share. Those 2 shares sum to 1. And these are the shares which right now we'll see encompass your direct and indirect use of both of these factors. But so let's do that now.
Ravi, so just to
Yes.
clarify, so we know that the second row in your proof is true, and that's why we can deduct the first row, right, in your proof. So.
Yes, that's right. You could just start at the cost function and go backwards. Yeah, exactly. Exactly. Yes.
Is there any re-optimization of the inputs we think about when we think of the input-output matrices, or we just keep the input-output shares fixed and then think of the price changes? Because I would say that if intermediate input prices change, you probably switch from nylon to polyester or something like that, and your shares could move.
Right. So this same concern in principle could show up over here, right? So as the price of labor goes up or the price of capital goes up, you might want to switch to the other input. But we use constant shares. Where does the non-constant share part of this turn up? Well, it would turn up in a second order approximation of this equation. And I think you guys at times have done some calibration exercises where it's really hard to get second order effects to matter that much. Sometimes they do, and you want to look at them. And there's cases where you have huge commodity price movements. Let's say, for example, in the late 70s, gas prices went way up. Producers started making cars that used a lot less gasoline. They got much better miles per gallon, and there were shares that meaningfully changed in the data. And so over periods like that, very large price changes, you might want to at least think about it. But at least to a first order, that effect won't matter. And that's what we kind of see in these equations for prices. Now for quantities, if we have time later, we'll see how substitution of the sort you're talking about comes in.
But Murphy, I think, when he uses delta, he always means a derivative.
Yes.
So there are no second order terms.
Gotcha. Okay. I often think about this as like a log linearization, but yes, if we're thinking about infinitesimal changes, then yes, this is exactly right. That's right. Okay, so where were we? Right. So now we want to think about what these shares are. And so the first fact I want to mention, this may have come up for you guys before in a statistics class, is just as for x less than 1, you have this fact. So everyone remembers this fact about geometric sums. The same fact is true for well-behaved matrices that you can invert of the kind that we have here. So you'll have, now we're starting on the right-hand side, kind of moving left. I minus phi inverse equals I plus phi squared, so on and so forth. Okay, so